Let's talk about electrostatics. So what exactly is electrostatics? What do you think about when you hear the word electricity? You think about charge, or at least that's what I think of. I think of charge, right? Like charging your phone, you use electricity for that. Static, well, that just means that it ain't moving, so it's not moving. So electrostatics basically deals with charges that aren't moving. Now, what exactly is a charge? Charges are kind of like another property of matter. They allow things to repel each other and attract each other, but in another type of force, another type of way. And so we can think about the atom, right? Hopefully, y'all know, or at least heard of, what an atom is. So, in an atom, you have the nucleus, and the nucleus is going to be composed of neutrons, which I'll just put N here, and protons, which I'll put a P and a plus here. Protons are positively charged, neutrons are neutral. And orbiting this atom, there are going to be electrons, which are negatively charged. Okay? So that's basically the basic model of the atom. And so for now, let's keep this pretty simple. We can say that a proton has a +1 charge, right? It's positively charged, so I'll just say it has +1 charge. Electrons, they're negatively charged. I'll just say they have a -1 charge. And neutrons, they have no charge, so they're just neutral. And so that's basically the foundation upon what we're going to build upon. Okay. What you need to know is that if you have two charges, let's say like charges, okay? So let's say if you have a positive charge and a positive charge, they will repel each other. However, if you have opposite charges, so a positive charge and a negative charge, they attract each other. So like charges repel each other and opposite charges attract each other. And we are going to be using this concept to talk about electric fields. Imagine if you have a charge in the center, all right, just in the center of this screen right over here. And imagine if you placed a test charge. So I'm going to be placing a test charge right over here to the side. A test charge. Okay? And this test charge right over here is going to be positively charged. You always use a positive test charge, okay? So imagine if I have this charge in the center and I'm trying to see what will this test charge kind of feel from this middle charge right over here. And like we said before, opposites attract, right? So this test charge is going to be opposites attract and like charges repel. So this test charge right over here is going to be repelled from the center charge, right? Now imagine what would happen if I just added this test charge, but I put them everywhere. So imagine if I put this test charge here, it would be repelled from this middle charge. It would go away, right? Same for here. These two positive charges, they repel each other, they go away. And you can see that kind of at every point that I put these positive charges on, they're going to be repelled from the middle charge. And so this is the idea of an electric field. It's basically just imagine a scenario where you have these test charges that surround your sort of central charge. What's going to happen to the test charge if you place it around it? And so that's basically the general idea. It sounds kind of too simple to be true, but I'm telling you, it's all there is to it. Right? We can do another example. Let's say instead of a positive charge in the middle, I have a negative charge. So imagine what happens if I have a positive test charge, right? So this right over here is my kind of central charge, and this is my positive test charge. What would happen if my atom in the middle right over here is negatively charged? What's going to happen? Well, opposites attract, right? So the test charge is going to be attracted to the negative charge in this case. And you can see that no matter where my test charge is, we're always going to get like a scenario where it's pointing towards the negative charge. And so what you realize is that, well, if you have a positively central charge, electric field lines are going to be pointing away from it because positive repels positive. But if you have a negative sort of central charge, electric field lines point towards it because, well, positive attracts negative. Let's say if I have a positive charge here and a negative charge here. Try and draw the electric field lines for this. Well, electric field, what you have to ask yourself is, if I place a positive charge anywhere around here, what's going to happen? Let's say if I place a positive charge here. Well, positive repels positive, and positive is attracted to negative. So this positive charge is going to try and go towards the negatively charged thing while going away from the positive one. If I place a positive charge here, it's going to go towards the negative one, right? Positive charge here, it's going to go away from the negative one, right? If I place a positive charge here, it's going to go away from the negative one, right? If I place a positive charge here, it's going to go away here. Because, of course, this positive charge right over here would like to go to the negative charge, but right now, if it goes this way, it kind of gets blocked by this positive charge. So the best that I can do is just go the opposite direction, right? If you have a positive charge here, it will go towards this negatively charged. And I can keep drawing this, but I think you get the idea, okay? And let's see if our diagram holds up with a simulation that I actually pulled up. So you have a positive charge here, which you can see kind of repels all these kind of imaginary test charges. But what happens if I place a negative charge here? Let's see if it matches up with what we had before. Whoa, right? This looks pretty cool, right? You have all the positive charges, test charges, imaginary ones, trying to go towards the negative side. Positive side, they're just going away from it or trying to go to the negative side. And so the way I like to think about this, and you're actually going to use this kind of analogy or this idea when you're going to like higher level physics, is that positive charges, they act like sources. It's like these lines are going to be diverging from them. Okay, so they act as sources of arrows. While negative charges, they act as sinks, right? They kind of absorb these arrows, right? So they kind of act like a sink, right? They absorb this stuff. And so sources and sinks, that is one good way to think about this. Now, remember when I said that protons have a +1 charge, electrons have a -1 charge? That's actually a little bit of an oversimplification. So this is just kind of to make things nice and easy to understand. But the reality is that charge is measured in the units called coulombs. And this +1 and this -1, they refer to the elementary charge. Okay. And the reason why you use this +1 and -1 elementary charges to represent protons and electrons is because one elementary charge is equal to 1.6, and this is on your reference table, by the way. So it's 1.60 times 10 to the negative 19th charge, or 1.06 times 10 to the negative 19th coulombs, right? And so you can, and electrons, that would just be negative 1.60 times 10 to the 19 coulombs. So just writing it out as, elementary charges, it just makes things a lot simpler because you don't have to, deal with these annoying kind of scientific notations and all that. So that's just all. But you need to know how to convert from elementary charges to coulombs. So let's say if I have, 2 elementary charges, well, all you just have to do is use this conversion factor, right? I have 2 elementary charges, so I know that if I had 1 elementary charge, that would give me 1.60 times 10 to the negative 19th coulombs. And so the elementary charge unit cancels out, so we're going to be left with coulombs, and so I get 3.6 times 10 to the negative 19th coulombs. And that's going to be my answer, okay? Another reason why elementary charges are useful is because, well, I can't have half a proton, right? So for example, for protons, right? I can have 1 proton, I can have 2 protons, I can have 3 protons, but I can never have half a proton, right? That does not make any sense. So what you actually find out is that if you're trying to represent like a charge, it's always going to be like a multiple of the elementary charge, or this 1.6 times 10 to the negative 19th coulombs. So here's like an example problem. I'm sorry if like the font is like this because that's just the default font of this whiteboard. So a small metal sphere has a total charge of negative 4.8 times 10 to the negative 19th coulombs. And total charge, you can kind of think about this as like the net charge, I guess. Right. So this small metal sphere has a net charge of negative 4.8 times 10 to the negative 19th coulombs. Notice how that's a multiple of the elementary charge. And so how many excess electrons are on the sphere? Well, I know that my charge right over here is negative 4.8 times 10 to the negative 19th coulombs. And I know that 1.6 times 10 to the negative 19th coulombs. I know one elementary charge is equal to that, right? So notice how the coulombs cancel out, right? I'm just converting from coulombs back to elementary charges. You're going to get negative 3. Now, what does this answer mean? Well, we know that this sphere is going to be negatively charged, of course, right? Because we have a negative 3 elementary charge. So the sphere is going to be negatively charged. And this 3 right over here, this negative 3 represents that we are going to have 3 electrons extra. All right. So the fact that it's negative tells us that, well, we're going to have a negative electron. And the fact that there's 3 of them tells us that we're going to have 3 of those negative electrons. And so how many excess electrons are in the sphere? It's going to be 3 of them. Okay. Notice how this doesn't tell us the exact amount of protons and electrons that we have. All this is saying is the amount of excess electrons. That's the key word. So you can have, let's say, 24 protons on the sphere and 27 electrons. Or you can have, let's say, 30 protons and 33 electrons. We don't know the exact amounts, but all we do know is that there's always going to be 3 extra electrons, right? We're going to have 3 excess electrons than we are protons, right? Because we have 3 more negative charges than positive charges, but we don't know the exact kind of ratio of positive to negative. So that's an important thing to know with these questions. If it's asking for excess, it's just the excess. Now, I have 2 positive charges separated by distance, and I want to know, well, what's the force that this charge feels because of the other positive charge? Because these charges are both positive, we know it's going to be a force of repulsion, but how much, right? What is the exact amount of force they're feeling? And we know that the forces are going to be equal because of Newton's third law, right? So action-reaction. The force that this object exerts on this object is going to be the same as the force of this object on the first object. So in a way, they're both equally repelled by each other. Now, the way we quantify this is doing something called Coulomb's law. And Coulomb's law pretty much states that the electrostatic force between 2 objects is going to be equal to the charge of the first object times the charge of the second object divided by the distance squared. And all of this is going to be multiplied by this constant K, which is the electrostatic constant. This is in your reference table, and the formula should be in your reference table as well. So if you scroll all the way down here, this is Coulomb's law right here. And so let's do an example problem. I'm getting lazy. I got GPT to generate me this. 2-point charges are placed this many meters apart in air. And these are the magnitude of the 2 charges. The 2 charges. You want to find the magnitude of the electric force between them. So Fe. And is the force attractive or repulsive? We can answer question B first. Think about this conceptually. You have a positive charge. You have a negative charge. What are they going to do? They attract each other. And so the force is going to be attractive. To find the magnitude of the electric force, it's going to be equal to our Coulomb constant, which if we scroll all the way back up, it's going to be equal to 9 times 10 to the 9 newtons times meters squared divided by Coulomb squared. So 9 times 10 to the 9 newtons meters squared divided by Coulomb squared times the magnitude of charge 1. So charge 1, or actually, times the magnitude of charge 2. So when we're trying to find out the magnitude of the electric force, this magnitude sign basically just means that we don't have to care about the sign. okay, it's all going to be positive, okay? So we can kind of ignore this negative sign. It's going to be positive, right? So it's going to be positive 3.0 times 10 to the negative 6, and then divided by the distance squared. So 0.30 squared. Okay, so put this into the calculator, and I got 0.60 newtons as my answer. And that makes sense, right? Because if we're dealing with forces, force is measured in newtons, right? You see how the units, right? So right over here, 2.0 times 10 to the negative 6 coulombs. This is also in coulombs. So notice how the coulomb squared is canceled out with these 2 coulombs. And notice how the meter squared on the denominator, right? Because it's 0.30, right? It's the distance squared. So it's 0.30 squared, aka meter squared. The meter squared cancels out on the top and bottom. So you're just left with the newtons, okay? For like these regions problem, they're always going to be asking for this magnitude. Magnitude means you just want to find out how much force is being exerted between these two, right? You don't care about the sign of, this or that. You only care about the magnitude. When you are asked if the force is attractive or repulsive, then that's when you bring in the signs. Let's talk about charging by induction versus conduction. Charging by induction involves placing a charge near an object, but not touching it. So for example, let's say if I place a negative charge near this object right over here. So there's like a charged lollipop. Okay. I place this positive charge near this object, which has both positive and negative charges. What's going to happen to this object? Well, positive charges get repelled by this positive charge. So you can think about them as moving away to the back, right? They're trying to move away as far as possible to the object right here. So if I draw what this object looks like, right, you would imagine that after I placed this object close to the other object and not touching it, all the positive charges would be kind of near the back, right, trying to get away from it, while the negative charges would come to the front because the negative charges are attracted to the positive charge. And so this is charging by induction. It's basically when you place a charged object close to another object, but not touching it, and it causes the charges to kind of like separate, I guess. So you have the positive charges in one area and the negative charges in another area. And when this happens, you say that the object is polarized, right? So that's pretty much it for charging by induction, okay? And if you were to place a negative charge here, I mean, it would just kind of be the same thing as this, except here it would be positive and there would be negatives in the back. You can actually form an attraction if you're neutral. I know that sounds crazy, but if you have a neutral object, like what I have here, right, notice how I have an equal number of positive and negative charges. But notice how this object still becomes polarized, right? If I place this positive charge near it, this object still becomes polarized, right? It's still attracted because all the negatives go to one side, all the positives go to another side. So the key thing to note is that if I have a positive charge, then I can make a neutral object. Or I can make a negative object, of course, right? If I have a positive charge, I can make a neutral and a negative, charged object attracted to it via induction. And likewise, if I have a negative charge, right? And let's say this is my sphere originally, so I have a mix of positive and negative charges. All the positives go to the front because they're attracted to the negative, and all the negatives go to the back. But notice how this object is still neutral. So when you have a negatively charged thing, well, think about it. Neutral objects can be polarized, and they can be attracted to this, right? But in addition, you can also just have a positive. You can also just have a positively charged thing that's attracted to it, because opposites attract. Okay? Conduction does involve touching. Okay? So it's when you have a charged object, and let's say this is filled up with positive charge, and you purposefully touch it with another object. So this object right over here could have a mix of positive and negative charges, But this case is when the two objects do touch each other. And in this case, when charges touch each other, charges like to disperse outwards. Okay, so think about it like this. Okay, and you might be given a question like this on the regions. All right, so notice how this object right over here has a net charge of 0. Okay, so the charge of this object, I'm just going to say it's 0. And the charge of this object, the net charge, that's going to be a positive 4 charge. So what charges like to do is they like to disperse. Okay, they like to mix. Because, well, think about it. If I have 4 positive charges in kind of one area, well, that's going to be kind of unstable, right? All these charges want to repel each other. They want to spread out so that, well, they're not as repelled to each other, as if they're just stuck in this spot. And so what's going to happen is 2 charges are going to go to this sphere, and 2 charges, you can think about it, are kind of going to stay here. Okay? The charge spreads out so that the resulting kind of configuration has an equal amount of charge, net charge. Okay? So charges like to spread out so that the resulting configuration has the same charge. Okay? And another way to put this is that, well, the resulting charge is just going to be the average of the 2 net charges on the object. So if I have a +4 charge here and a 0 charge here, the resulting charge is just going to be the average of these 2 numbers, which is a +2 charge. Okay? Let's do another example. If I have, I'm too lazy to draw it out, but you get the idea, right? If I have a +16 charge, and let's say if I have a -8 charge, what's going to happen is that, well, the resulting configuration, well, it's just going to be the average of these 2 numbers. And the average of 16 and -8, that's just going to be a +4. +4. Okay? So that is the way you do these questions. You just take the average because charges like to spread out. And you can be given this in coulombs or elementary charges, but the key word is average. So conduction, that's basically all there is to it. But for induction, there's actually a couple more things you got to realize. So let's say if you have 3 kind of balloons, and these 3 balloons are all touching each other. Okay? So just draw it like this. So they're all going to have a neutral net charge. Okay? So I'm just going to draw a couple positives and negatives. Because they're neutral, notice how the charge distribution is going to be equal, right? There's going to be the same amount of sort of positive here and negative here that I drew for all of them. Okay, so all of them are neutral, and let's say I place a negative charge close to the first balloon, but I don't touch it. What's going to happen? Well, all the positive charges are going to get attracted to it, and all the negative charges are going to move back, right? So this idea of charging by induction extends beyond just one item, right? So you can see that the resulting image is going to be all the positive charges, they want to get close to the negative one, and then the negative charges are going to fall back because of the repulsion. So grounding, let's talk about this. This is like an extension of the induction that we're talking about. Grounding refers to essentially we're connecting whatever object we have to the earth or to the ground, okay? And what that allows us to do is it allows the charged particles to flow in or to flow out. So in this case, look, we have this negative charge here, and we are charging our connected object, so these 3 balls right over here, via induction. So we're bringing it close, the positive goes here, but then the negative charge, they want to run away, right? The negative charges, they are running away from this negative charge because of repulsion. And so what happens is, when you allow these negative charges to essentially escape, right, you ground it to the earth. And so these negative charges are just going to travel, down this grounding. And so what happens is you're going to end up with less negative charge than before. So if I connect this to the earth, right, the negative charges escape. And so if I then remove this grounding right over here, the resulting charge would be positive, right? Because you allowed those negative charges to escape, okay? And likewise, if this was positively charged, well, think about what would happen here, right? So let's say if this was positively charged. Well, what's going to happen is you would have negative charges in the front because opposites attract. So negative charges here, and then the positive charges would be in the back. And I ground this to the earth, okay? Or to the ground. Well, if I have positive charges in the back, what do positive charges attract? Positive charges attract negative charges. And so negative charges are actually going to rush in from the earth from the ground, and there's going to be more negative charges here because they're going to get attracted to positively charged things. And so if I then remove the grounding, well, look at the net charge. Now we have more negative charges than positive charges. And so the key thing to note, the key summary, is that when the rod nearby is positively charged, electrons enter, and that makes the final charge negative. But in contrast to that, if the rod nearby is negatively charged, electrons leave due to the repulsion, and the final charge would be positive. Now let's talk about electroscopes. So I'm using the SimPop simulator, and I'll give you the link to that in the description. And so what is an electroscope? What explains it really handily here? It's used to detect the presence, magnitude, and type of electric charge on a body. So it is composed of a metal disc right over here, and these are the leaves of the electroscope. And so you can charge this by induction, by placing it close to the electroscope. And notice how a positive charge leads to a negative charge coming up to the disc. And so, well, what happens is that, well, the rest of the positive charges, they go down to the leaves. And because positive charges, like charges repel, the leaves spread out, okay? And the same is true if you place a negative charge. Because a negative charge attracts positive charges, the positive charges come up the disc, while the negative charges kind of go to the leaves, right? And they repel each other, which makes the leaves spread out, and that's how you know that there's a charge there, okay? If you place a neutral charge, I think just the key to remember is that neutral charges for electroscopes, they don't do anything. You can also charge this by conduction. Notice how we're charging by induction by placing it close to it. We can also charge it by conduction. So what do you think is going to happen if I take a positive charge and I place it in a neutral object? What's going to happen? Well, remember how charges like to spread out. So if I place a positive charged object to a neutral object, it's going to become positively charged, which is exactly the case here. And so what happens is the positive charge spreads everywhere, and it gets to a point where everything basically has a net positive charge, and so the leaves are going to be positive and they spread out along with the disc. Okay. And likewise, if I have a negative charge, I'll just fix this. Okay. And likewise, if I have like a negative charge here, right, and I charge it by conduction, by touching it, everything becomes negative. And so what happens is the leaves become negative and it spreads out. Okay. Now on, a multiple choice quiz, your teacher might say, how would you charge an electroscope, I guess, positively by conduction? Well, then place a positive charge. If you want to charge an electroscope negatively by conduction, place a negative charge. If you want to charge an electroscope positive by induction, by placing it near, you use a negative charge, right? And to charge an electroscope positively by induction, aka to make the disc positively charged, well, you place a negative charge near it. And when you want the electroscope to be negatively charged by induction, well, you would use a positively charged rod. Okay? Okay, we're going to move back a bit, back to the electric fields. Okay? This is a pretty good review, but this time we are going to be dealing with plates. So these two plates are going to be parallel to each other. One is going to have a positive charge. The other one is going to have a negative charge. Now, the first thing I would like you guys to do, guys and girls, is I want you guys to draw the electric field lines for this. So where would the electric field lines point to? Well, remember, electric field lines, they always point from positive to negative because, well, a positive test charge always gets attracted to the negative thing. So it's going to look something like this. And because these two plates are actually parallel to each other, the electric field strength, so there's something called the electric field strength, essentially how strong is this electric field, and this right over here is going to be uniform, okay? The strength of the electric field is going to be uniform. So essentially, the electric field strength, we can define this electric field strength as essentially the force per charge. So if I place the charged object inside this electric field, like right over here, let's say this is a charge of 2 coulombs, and let's say that this charge, when placed here, experiences a force of 400 newtons. Well, then the electric field strength would be, well, the force, 400 newtons, divided by the charge. And you would get just an electric field strength of 200 newtons per coulomb. All right? And if, let's say, you had a higher force, let's say instead of 400 newtons, your charge experiences 1,000 newtons. Well, then the electric field strength would just be 1,000 over 2, which is 500 newtons per coulomb. So it's kind of like the push per charge, right? Because if this was a positive charge, well, then this 500 newtons per coulomb is basically saying for every charge, for every coulomb in this charge, right, it's getting pushed more, right? It's getting pushed by 500 newtons instead of just 400 newtons or 300 newtons, right? It's a stronger strength. What you notice is that mechanics and electrostatics, their formulas are kind of connected to each other in a way. Like, you can think about electric field strength being, the electrostatic force divided by the charge. But another way, or, kind of another formula that might help you think about that better is, well, gravity, right? The acceleration due to gravity, that's equal to, well, your weight divided by the mass, right? And so another formula, you might have seen this, Coulomb's law, Q1, Q2 divided by the distance squared, or, they might put R squared. Well, what's that similar to? Well, in your reference guide, there's a pretty clear one that this is similar to, that you've definitely encountered before, and it's this one, right? The force due to gravity is equal to this gravity constant, I'm just going to call it that, times the mass 1 times mass 2 divided by R squared, right? The only difference is that while positive and negative charges can repel, but gravity, it's only attraction. But, it's very, very similar. There's a lot of connections there. So I want you to recall this formula. The change in potential energy is equal to the mass times acceleration due to gravity times the change in height. So for example, if I was levitating up here, I would have a certain height relative to the ground. And just by existing here, I'll have a potential energy, right, associated with that height. And likewise, if I'm down here, right, there's going to be a height associated with that. And this height represents, potential energy at spot B, let's just say. All right, so this is the potential energy at spot A, and then this is the potential energy at spot B. So that means that the change in potential energy just represents kind of this change in height right over here, right? So the mass times gravity times the change in height gives me my change in potential energy. Now, the convention here is that the potential energy at the negative plate, right? So we can connect this to like electric fields with parallel plates, right? It's just like how when you define potential energy, it's potential energy relative to the ground, right? This is your reference point. And for this video, we're going to define that ground, quote unquote, as the negative plate. So potential energy at the negative plate is 0. As you move up, the potential energy increases. So the closer you are to these positive plates, the more potential energy you have. Now, it's going to be a little bit different, obviously, because we're not going to be dealing with height. We're going to be dealing with essentially distance from the negative plate instead of height. And so the formula for potential energy in electrostatics, it's going to be equal to the charge, which you can think about as mass, times the electric field strength, which we thought about that as gravity before. And instead of the change in height, it's just going to be that displacement or that distance away from the negative plate. And so we can actually write that as the change in potential energy, because, well, if this right over here is 0, and let's say I place a charge, or sorry, this is 0, right? I'm at the negative plate. I place a charge like right over here. Well, then this displacement kind of represents that change in height, right? So we can write the change in potential energy is equal to charge times the electric field strength times the displacement. And so the definition of voltage, and voltage, you can think about it as a difference in electric potential. So what do I mean by difference in electric potential? Well, it's just going to be the difference in potential energy. So, difference in potential energy divided by the charge. So it's like the energy per charge, okay? And so this is the important formula to know. And another way to write it is negative potential energy. So this is just another formula that you might remember from kinematics and stuff. So negative potential energy is equal to the work. So voltage is also equal to the negative work divided by the charge. And so you actually have this in your reference table. So you actually don't have to memorize this. So another way to define the electric field strength is voltage divided by displacement, okay? And actually, another name for the unit of voltage is volts. So recall that voltage, if it's negative work divided by the charge, well, work is in joules, right? It's like energy. Charge is defined in coulombs. Joules per coulomb is a volt, okay? Now, the regions actually, what I'm talking about here when voltage is equal to negative work divided by charge, what we're saying is that the electric field, that's going to do work on the charge. So hence, because the arrow is pointing downwards, we're going to try to go from an area of high potential energy to low electric potential energy, right? So hence your voltage is kind of like decreasing, right? You're going from high to low. But in regions physics, you might have saw the formula before. The work is going to be positive, and the reason why is because usually you're not going to be dealing with work from the electric field itself. Usually you're going to be dealing with like an external kind of work, right? So this is work done by an external force. So maybe it's like somehow the charge gets like pushed upwards instead of getting pushed downwards, and in that case your potential energy would be increasing, right? Going to kind of like a higher height. And so that's why in the regions formula, you don't see that negative sign, because it's external work compared to the work done by the electric field itself, okay? Just wanted to get that clear, but let's actually prove why this is the case. Work, well, that's equal to force times displacement divided by charge. Well, notice I have force divided by charge up here. And where do I see that? That's equal to the electric field strength, right? And so I can write this as the electric field strength times the displacement is equal to the voltage. And if I divide both sides by displacement, I get my formula up here.